Solving systems with matrices. Here is a diagram of two tables for the attendance of club meetings in the 2002 school year and the 2003 school year. We are demonstrating moving it from tabular format to a matrix format. All right, you can see the same numbers in the same spot that they exist in the table. So what is this matrix thing? A matrix is simply a table without labels. To name a matrix, you use capital letters. An element is each entry of a matrix. So all the numbers you saw is considered an element. The dimensions of a matrix depends on the number of rows and the number of columns. When determining the dimensions of a matrix, always remember arc. Matrix are named with capital letters, and you mention the rows first, followed by the columns. So arc, capital letter for your name, rows first, then columns. Another way of looking at it is matrices are really cool. So back to matrix A and matrix B again. Both matrices have the same dimensions. They are 3 by 4 matrices because they have 3 rows and 4 columns. Rows go across, for those who forgot, and columns go up and down. A linear equation in 3 variables is a linear equation written in the form ax plus by plus cz equals d. A, B, C, and D are real numbers. A system of 3 linear equations is a system made up of 3 linear equations in the same variable. The solution to a system in 3 variables are the values of the 3 variables that make each equation true. Lastly, we have an ordered triple, which is a coordinate on a 3-dimensional graph where the 3 that represent the 3 variables that are the solution to the system. So when you write your ordered triple, make sure you put it in alpha order. So x, then y, then z. When solving with systems with matrices, there are various ways out there. There's augmented matrices, inverse matrices, or Cramer's rule. But today we're going to focus our attention on augmented matrices. An augmented matrix contains the coefficient matrix with an extra column containing the constant terms. So in our first example, it wants us just to simply write the augmented matrix for this system. So that means take all the numbers in front of each variable and take them away from the variable, as well as the constant, whatever comes after the equal sign. Make sure your equations are always written in alpha order or standard form first, and then write your augmented matrix. So this one would look like so. 1, 4, 9. 1 was in front of x, 4 was in front of y, and then 9 was your constant. And then -6, 7, -2. So again, all you're doing is when you're writing a matrix is taking the numbers away from the variables. Identity matrices. An identity matrix is a matrix that has a diagonal of 1s with 0s on each side. For example, you have the 2 by 2 identity matrix on the left and the 3 by 3 identity matrix on the right. So again, 1s are in the diagonals and then 0s are everywhere else. We're going to be using augmented matrices with our calculators to solve the systems. And here are the steps below. So now we're going to practice. We're going to solve the system 2x plus 5y equals 7, x plus 4y equals 2. The first thing we need to do is write the augmented matrix and enter it into the calculator. So the augmented matrix would be 2, 5, 7, followed by 1, 4, 2. Again, just take all the numbers from the equations, leave them in the same order they appear. Just be careful that your equation is always written in standard form first. Standard form means x before y, and make sure x and y are on the same side of the equal sign. Then you find the reduced row echelon form or RF form of the matrix. So this is the output of the calculator. Let me demonstrate how that works. Hold on one second. So the first thing you would have to do is locate RF on your calculator. To do that, we would hit second x to the negative 1 power for the matrix menu. Go to math and then hit alpha apps, and then RF will appear on your screen. Now we need to insert our augmented matrix. So to do that, we would hit alpha, zoom, and now we need to tell it how many rows and how many columns we need. And you have to use the up and down arrows to do that. So as you can see, I was originally on OK, so I need to hit up to get to the row column. That sounds, the row numbers, there we go. So this matrix has 2 rows, so let's highlight, put the box over 2, and hit enter. Then hit the right arrow to get in to see the column numbers, and there's 3 columns. So put the box on 3, hit enter. Now go all the way down to highlight OK again and hit enter. So now all we need to do is type each number, hitting the right arrow after each one. So starting with 2, arrow, 5, and then 7. And then arrow again to get down to the bottom row. So 1, 4, 2. Hit enter. And now you see the RF form of the matrix that we entered. So let's now discuss how to interpret this output. Like, what does this really mean? So what you should have noticed on the left-hand side of the dotted line was our was an 2x2 identity matrix. The identity matrix again has ones on the diagonals with zeros everywhere else. And then you had your constants on the right still. If you were to take that matrix and rewrite it back in equation form, it would look as follows. X plus 0y equals 6. 0x plus y equals negative 1. If you simplify it, it would simply read x equals 6, y equals negative 1. With that being said, we have our solution. We have our x value, we have our y value. So the solution to the system is 6, negative 1. Yes, it is that easy. Lifesaver, I know. So we could do the same thing with any size system. So on this linear system here, it's a 3 variable linear system, and it's a 3 equation linear system. So we got to solve for x, y, and z. The first equation, 3x plus y plus z equals 14. The second, negative x plus 2y minus 3z equals negative 9. 5x minus y plus 5z equals 30. So the augmented matrix for this is shown below. 3, 1, 1, 14, negative 1, 2, negative 3, negative 9, 5, negative 1, 5, 30. And now put that into the calculator to get the RF form of this matrix. So again, to find RF, it was second, x to the first negative first power, math, and then alpha apps. To put our matrix in there, we would hit alpha zoom. Now we need to tell it, oops, we need to tell it how many rows we have, and we have 3 this time. And we have 4 columns this time. And hit OK. Now enter each element. 3, 1, 1, 14, negative 1. Whoa, too many ones. Delete that one. 2, negative 3, negative 9. 5, negative 1, 5, and 30. Double check to make sure you've entered all the data properly before you hit enter so you get the right answer. And there's my my RF form of this matrix. Again, you notice I have the identity matrix on the left side of the dash. It's the 3 by 3 identity matrix. So it's always in alpha order based on everything else. So this is X, this is Y, this is Z. And you write the solution in alpha order as well. So that means the solution would be 1, 5, 6 for this system. Last but not least, just if you're using elimination method or substitution or matrices, and your output looks similar to these two examples, there's two outcomes possible. So when you have a false outcome like 0 equals 102, that system will have no solution. So in other words, if you go back to thinking when we did our graphing methods, the systems with no solutions were parallel and never, meaning they never cross. But if you get something that is true, like 0 equals 0, this represents infinitely many solutions. So if you go back to when we were graphing, these were lines that coincide. In other words, the same exact line. So just be mindful that those outcomes are possible when you're solving algebraic systems or systems algebraically. So don't be nervous, don't be scared. Just simply say that this system has no solution or this system has infinitely many. Otherwise, if you do get something for X and you do get something for Y, or even Z for that matter, then that system has one solution. This concludes your lesson for today.